Hello, and welcome to our latest installment of the webinar series towards a durable understanding of soil carbon as a tool for climate adaptation and mitigation. I'm Eric Slesarev. I'll be your host today. And the question that we'll address today is a complex and somewhat abstract one, but it's really important to this whole debate. We're going to address the question of how does the impermanence of soil carbon storage affect Earth's climate? We have two speakers today. The first speaker we'll hear from is Allegra Mayer, who is currently a postdoc at Lawrence Livermore National Laboratory. She completed her PhD at UC Berkeley in the Environmental Science Policy Management Program in 2021. And was also a Lawrence Graduate Research Scholar during that time. Our second speaker today will be Susan Crowe, who's an Associate Professor of Soil Ecology and Biogeochemistry in the Natural Resources and Environmental Management Department at the University of Hawaii, Manoa. She's involved in a whole range of task forces and organizations like the Greenhouse Gas Sequestration Task Force for the state of Hawaii and the North American Carbon Program, for instance, that address the role of soil and ecosystems in Earth's climate. All right, so we'll start by hearing from Allegra Mayer, who will talk about her work relating soil carbon to climate change from an atmosphere-based perspective. And take it away, Allegra.
Thanks, Eric, and thanks so much to AGU and to ISCN for having me. I'm really excited to be here and really honored. So I'm going to present some of my own work co-authored with Zeke Housefather and Andy Jones and Wendy Silver. And I'm also going to be touching on some newer papers that have come out on this topic. And I'm hoping this will be a nice complement to what Professor Susan Crowe is going to talk about later. So past ISCN seminars have centered on the soil system, but today I'm going to zoom out and we're going to take an atmospheric perspective on soil carbon and how that soil carbon is in relationship with climate. So why center the atmosphere? Well, if we're thinking about climate change mitigation and the relationship between climate change and soil carbon, we need to consider the amount of carbon in the atmosphere, because it's not just the increase in soil carbon itself that cools the climate, but rather the transfer of carbon to soil from the atmosphere. So in the end, it's the decrease in atmospheric carbon that mitigates future warming. This figure is showing net greenhouse gas emissions, the y-axis over time on the x-axis, and each of these colors represents a different shared socioeconomic pathway, or SSP, for the future, with the future warming outcomes here in orange on the right. And so international agreements pretty much all target 2 degrees Celsius or less of warming as an ideal outcome. But all of the shared socioeconomic pathways that limit warming to less than 2 degrees show that not only negative emissions in general are going to be required, but actually net negative global emissions. So anything below this horizontal line is showing net negative emissions. And that means that carbon removal is occurring alongside reduced or zero fossil emissions. So how can we reach this goal of net negative global emissions? Well, the IPCC Working Group 3 report that just came out last week shows that the greatest potential for net emissions reductions, which is here on the x-axis, is going to be in switching from fossil energy, wind and solar energy. And the great thing about this is that there are also low costs associated with this switch. So in this figure, blue represents low or zero lifetime costs, and the redder the bar is, the more expensive this solution would be. This figure makes it quite obvious that the lowest hanging fruit with regard to reaching net zero or negative emissions is going to be in switching energy sources from fossil to wind and solar. But interestingly, the IPCC also still continues to consider soil carbon sequestration in agriculture, here in green, as one of the next biggest opportunities for climate change mitigation. But we're also acknowledging that there is going to be an economic cost and uncertainty associated with this. So let's talk about carbon sequestration in agriculture. First, we need to step back and define what we mean by soil carbon sequestration. So carbon sequestration, in the context of this talk, occurs whenever atmospheric carbon inputs to the soil exceeds the loss of soil carbon. So that could be either through respiration or through other processes. So whenever the flux of carbon into soil is greater than the flux out of soil, this results in an expanding soil organic carbon stock. Now, plenty of field studies have shown that we can manage soil, affect fluxes of nitrogen and carbon, and increase that transfer of atmospheric carbon to the soil. But we also know that the potential of this negative flux is nowhere near the size of the annual flux of anthropogenic greenhouse gases to the atmosphere that continues to be emitted each year. So we need to ask, is there any future scenario in which it's possible to maintain a rate of carbon sequestration in agricultural soil that could measurably reduce global temperatures? Well, in order to answer this question, I'm going to address this from 3 different levels of complexity. First, we're going to look at the technical feasibility. What rate would be required? What rate of sequestration, what rate of carbon removal from the atmosphere would be required to kind of reach a measurable change in global temperatures? Then we're going to add another limitation. So what if carbon sequestration is only effective over a limited amount of time? And then finally, we're going to add loosen the assumptions even further and ask what happens if carbon sequestration can be fully reversed in the future. Let's start with the technical feasibility. To understand the rate of atmospheric carbon that must be removed in order to see a change in global temperatures, we used a reduced complexity model to simulate climate responses. This model is called SimMod. It was developed by my co-author Zeke Hausfather. And it's a climate simulator, an emulator that produces global results consistent with fully featured climate models from the CMIP-5 run. But it has the advantage that it can be run thousands of times faster. So in this figure, we're showing the temperature anomaly output by the CMIP-5 models from the AR5 IPCC report here in gray, with the ensemble mean in black. And you can compare that with the SimMod output in red. And you can see that the SimMod output actually matches very closely the ensemble mean of those CMIP-5 models. And so we simulated the outcomes for carbon sequestration under 4 different emission scenarios, or representative concentration pathways, RCPs. So under the first scenario, the low emission scenario, which is RCP 2.6, we expect that warming would reach about 1 to 2 degrees Celsius by the year 2100. Whereas in the high emission scenario, which is RCP 8.5, and there's 2 scenarios in between that, we would expect total warming to increase by between 3.5 to 5.5 degrees Celsius by the year 2100. Those are the 4 scenarios that we modeled. We used SimMod to calculate the entire solution space for the warming reduction that could occur due to a sustained sequestration rate. So our sustained sequestration rate is here on the y-axis. And we evaluated this over time. And we used 0.1 degrees Celsius as a benchmark. And that's labeled here in this white line. And it's kind of an arbitrary benchmark, but we're using it to represent a measurable decline in warming. So this is about 10% of the remaining allowable warming 2100 based on this RCP 2.6 baseline emission scenario. So how much emissions would be required? What's the carbon sequestration rate that would be required to reduce warming by 0.1 degrees Celsius? And what we found is that it would require less than a petagram of carbon to be sequestered each year through the end of the century in order to reach this temperature target. And I'm going to show you in a minute that actually this 0.69 petagrams of carbon per year is well within the range of published attainable sequestration rates that have been published at a global scale. And likely we can even go further than that in terms of annual sequestration rates. But there's some important background information that you need to know. So radiative forcing, which controls warming and cooling of the climate, is here on the y-axis. And what you can see is that radiative forcing does not respond linearly to atmospheric concentrations of CO2, which is here on the x-axis. So because the relationship is much more sensitive in a lower emission scenario, and this relationship is steeper in an atmosphere with less atmospheric CO2, you can see that the same reduction in radiative forcing, here this blue arrow, we want to see a reduction in radiative forcing, which leads to climate cooling, however requires a fairly small amount of CO2 to be removed in a low CO2 world. But if we compare this to what would be required in a higher CO2 atmosphere, that exact same radiative forcing reduction, or this cooling, would require a greater amount of CO2 to be removed for the exact same difference in climate. So if we compare the orange and the red, you can see that that red is much greater. So because of this nonlinearity of climate forcing, a warming reduction of 0.1 degrees Celsius in this low emission scenario that I showed you earlier takes about 0.69 petagrams of carbon of sustained per year of sustained sequestration. For that same warming reduction, you would require over 1 petagram of carbon per year in a high emission scenario. What this means is that we're going to get a much bigger bang for our buck by simultaneously reducing emissions. And that kind of points to this idea of a virtuous cycle, which is that the more emissions reductions activities take place, actually the greater the impact of a given land-based sequestration activity. So emitting less is actually going to increase the power of carbon sequestration to mitigate climate change. So for some context on that rate of sequestration briefly, we can look at a more recent study of a high complexity Earth system model outputs. And this 2020 study by Ito and colleagues used complex and updated Earth system models from the CMIP-6 runs to show that the assumptions for land use and emissions in an optimistic shared socioeconomic pathway, so this is SSP1, would result in a mean terrestrial carbon sequestration rate of about 0.6 petagrams of carbon per year on average through the century. So it wouldn't be constant, but that mean sequestration rate for all terrestrial drawdown would be about 0.6 petagrams of carbon per year. And so I just want to show you this to illustrate that the carbon sequestration rate I highlighted in that previous slide is both socioeconomically and biophysically possible. It's not out of the question. All right, so let's step back, and now I'm going to recenter soil for a second, because we want to complicate that question and ask what happens if carbon sequestration can't be sustained through the century as only effective for a limited amount of time. So centering the soil, we already know that there are multiple agricultural management practices that could lead to enhanced soil carbon storage, such as cover cropping, such as returning residues, for example. And so we synthesized published estimates of the global potential for carbon sequestration rates in both croplands and in grazing lands. And we calculated the potential climate impact of carbon sequestration through these existing low-tech agricultural management practices. And I want to say that, while the IPCC also focused on agriculture as one of the main high potential strategies for carbon sequestration, we're also focusing on agriculture because there's a vast land area that's managed currently under agriculture, and because it's managed, there's an immediate accessibility to change management in these lands. So that means that this global flux is actually it could actually be affected. But now, as soil biogeochemists, we know that increasing soil carbon sequestration rates with management are likely to not fully remain constant over decades, right? We know that shifting management can increase soil carbon over time. That's been shown in many studies. But as the soil carbon stock will increase, but will eventually likely reach a new equilibrium. So this figure is from a DayCent simulation of a one-time compost amendment to a range of soil types and climates in California. And the y-axis is showing just the newly photosynthesized soil organic carbon. That's due to the new management. And so if we're fully excluding any carbon that was added directly from the compost. And you can see that as we follow this new soil carbon stock over time, it's increasing over decades, and eventually it equilibrates in all of these soils. But what this figure is meant to illustrate is that the time it takes for a soil to reach a new soil carbon equilibrium is going to depend on a number of factors. It's going to depend on environmental factors, on soil properties, and on each soil's capacity to store more carbon. We also expect that that time it takes to reach a new equilibrium is going to depend on how long a management practice is sustained, and also it's going to, especially how long you sustain a management practice, is going to depend on economic and social and political factors as well. So there's a lot of unknowns here in terms of how long it's going to take to reach a new equilibrium, or what the potential maximum sequestration rate might be. So if sequestration rates could be sustained indefinitely, as you would illustrate here in the top, that change in soil carbon stock would continue to increase over time, perhaps linearly. But since we know that at least in some cases, there's not an indefinite increase in soil carbon stock, eventually this actual sequestration rate is going to approach zero as it reaches equilibrium. Because there are many possible trajectories towards which we could go from the initial sequestration rate towards equilibrium, we created this concept to simplify the math of it. So that we call it effective sequestration years, or effective sequestration time. And essentially, it's a simplified function. We're simplifying it as a constant sequestration rate with a cutoff point, with a step function. And we're calling this effective sequestration time whatever the integral of the curve is, as long as it's the same as this more complicated function. As long as these integrals are the same, we're sequestering the same amount of carbon, and this can simplify our calculations. We define effective sequestration years as the number of years of carbon drawdown that results in an equivalent net change in carbon as a trend, as equivalent to a trend of gradually decreasing sequestration rate. And since there are few rigorous long-term studies that have examined the dynamics of sequestration over the decades, especially not at an annual rate, and then we certainly don't have enough information to generalize across a global study. So we proceed with the analysis, make no assumptions about the shape of the rate of decline. Any of these are possible, but just imposing this idea of a limited effective sequestration. We calculate the impact of what a limited effective sequestration year could have on warming reduction to the year 2100. Effective sequestration years is here on the y-axis, and we calculated this, the solution space for this, for a sequestration rate up to a biophysical potential limit of global carbon sequestration rate, and that's here on the x-axis. And for context, I've added compiled published global rate estimates of carbon sequestration rate from agricultural soil management. And you can see specifically for croplands is labeled here in green, sequestration rates in grazing lands are labeled here in orange, and the combined potential of the two is labeled here in black. And since we put this together, some new studies have come out to estimate global potential sequestration rate, and they all fall within this range of combined potential rates. So we find that if we take, let's for example, take this high end of combined potential sequestration rate. And if you look at that, this mean upper range is about 1.78 petagrams of carbon per year of sequestration. And if we assume that this is effective for the next 85 years, this could remove enough atmospheric carbon to reduce global temperatures by 0.26 degrees Celsius in the year 2100. However, if we change our assumption to allow for the fact that that sequestration rate might not be effective for 85 years, but rather maybe only for 35 years, what would happen to the global temperature? Well, we'd still see that there would be a warming reduction would be much smaller, right? 0.11 degrees Celsius instead of that 0.26 degrees Celsius. And now you might be thinking, well, of course, a limited sequestration period is going to reduce that climate mitigation effect. But we also want to note that even for this limited effective sequestration period, we do still see this warming reduction of over 0.1 degrees Celsius. We want to show that limited sequestration periods can still have potential to make an impactful contribution to climate change mitigation. And like I showed earlier, not only is there uncertainty about the duration of effective sequestration years, but also, of course, about the policies and behaviors around the world that countries will adopt to fully avoid or eliminate fossil emissions in the future. And I've showed you before that background emissions matter. So I'm showing here that that combined biophysical potential from the literature here could reduce warming by 0.26 degrees Celsius in a low emission scenario, but that that warming reduction would be reduced to 0.14 degrees Celsius in a high emission scenario. So this is just again to demonstrate how avoiding emissions increases the mitigation potential of the biophysically viable sequestration rates. So this brings us to the question of what happens if we loosen our assumptions even further into the future? Will it still matter from a climate change mitigation perspective? So through the body of work I just presented, the key assumption was that there could be a continuous management with an intent to maintain sequestration rates over time. But what happens if carbon sequestered is totally reversed and re-emitted to the atmosphere? We know that soil carbon is vulnerable to disturbances, to climate catastrophes, or to changes in management. And so there is potential, of course, that all that carbon sequestered could be temporary. We can't guarantee that it will be there forever. But I do want to note on the side here that I don't yet know of any study that has definitively shown that the halting of an agricultural management practice has led to a complete reversal of all additional soil carbon stocks. And so if you, one of you listening today, do know of a study that's shown that, please let me know what that is. I'm really interested to read it. But let's just assume, okay, that it is possible that all of the soil carbon that was sequestered could be fully reversed and re-emitted back to the atmosphere. Well, fortunately, we have an idea of what could happen. There's a new paper out that just came out this year in 2022 by Matthews and his colleagues. And they used a medium complexity climate model to evaluate the temperature effect of carbon sequestration, assuming that all of that would be eventually reversed. I've illustrated for you here, this is their work here on the right, and I've illustrated for you their assumptions about carbon sequestration rate on the left. This is my illustration. And I just want to show you what their assumptions were. So they examined a few scenarios. In all scenarios, there was a limited effective carbon sequestration rate. It starts in 2020, and then the effective sequestration rate goes to 0 by the year 2056. And there's a few different sequestration rates, and purple is a lower carbon removal from the atmosphere, and the orange and blue show higher carbon removal. But in all scenarios, eventually, all of the carbon that had been emitted is eventually reversed and returned to the atmosphere by the end of the century. And so what they found when they looked at how that impacted global temperature is that even temporary carbon removal that's fully reversible could still decrease peak global temperatures, especially in the case, and actually only in the case, when fossil fuel emissions are simultaneously decreased. So this is in an SSP1 scenario, so an optimistic third socioeconomic pathway, or an RCP 1.9. So it's assuming that emissions are drastically reduced, and you can actually see that even with temporary carbon removals, this can contribute to a reduction in peak warming. However, if emissions continue to increase throughout the century, such as in an SSP2 or RCP 4.5 scenario, that temperature reduction is actually just delayed by a few years rather than fully reduced, rather than having the peak temperature reduced. This finding aligns with the conclusions from our study that I presented earlier, noting that reducing the rate of fossil fuel emissions immediately and drastically is pretty much the only scenario in which results, you can see an actual reduction in warming and of up to 0.1 degrees Celsius. Otherwise, maximum temperatures are just delayed given temporary sequestration. So there's a few messages I want you to take home today. One is that existing agricultural management strategies could measurably reduce global temperatures at peak warming, even if carbon sequestration is temporary or reversible. And the pros is that there's a lot of land area with immediate implementation possible. And most importantly, many of these practices that improve soil organic carbon in agricultural soil also provide other co-benefits that are important, including reduced erosion, increased water retention, or increasing yields. But the drawback of this as a mitigation strategy is that we can't guarantee permanence of soil carbon in the soil. So that leads me to the second take home, which is that we need to both avoid emissions and sequester carbon. And the benefit of that is that land-based sequestration strategies are much more effective at reducing global warming when it's combined with dramatically reduced fossil emissions. And this is partially because, for this reason, actually, carbon sequestration in soils shouldn't be considered a substitute for reducing emissions, because by nature, the durability of enhanced soil carbon is not the same as permanently avoiding emissions. And so capitalizing off of the false equivalence of the two might lead to actually greater harm with regard to the climate than good. And with that, I'd really thank you for your attention. I'm thankful to my co-authors and for guidance. And I'm really looking forward to the next talk and for any of your questions you might have. So thank you very much.
Wonderful. Thank you, Allegra. That was terrific. One thing I forgot to mention at the start is that attendees can post your questions using the questions feature in the GoToWebinar the sort of doc panel there. So take a look and post questions if you've got them. In the meanwhile, I'll relay some questions we received during registration. There were a lot of questions that were kind of tackling a similar topic, so I've kind of grouped them here. But Allegra, I'm wondering, based on your research related to this topic, what mechanisms in the context of carbon markets can be used to value soil carbon, given that it isn't permanent? What are the approaches that have been proposed for relating soil carbon to fossil carbon, given that they aren't actually the same? Is there a way around that problem?
Yeah, thank you for posing the last framing of that, because I'm actually not sure there's a way around that problem, and that's kind of what I want to emphasize in this talk. One of the mechanisms that's been used so far is to introduce this idea of a buffer pool, where you're paying for much more carbon to be sequestered than what you're allowed to then emit or what you're exchanging for. And I think that's better than nothing for sure, because of the vulnerability of soil carbon. But I am actually, based on what I know about markets and what kind of the exchange of and the durability of soil carbon, is that maybe an exchange of emissions for carbon sequestration through a private market or any kind of industrial marketplace is not necessarily the most effective way to get at mitigating climate change, but rather maybe a top-down type of mechanism is probably going to be more effective, some type of regulatory mechanism, or at least one that requires a given company, whoever the buyer is, to prove that they've also reduced or eliminated their own fossil emissions as well.
Thanks. I guess a follow-up question for me, just to clarify that, I specifically with regards to buffer pools, which for the audience, if you're not familiar with this concept, basically the idea would be that you do more than you would think you need up front, and so if you're paying for some practice that's in principle sequestering soil carbon, you'd pay for more of it up front, under the understanding that some of it would be rendered ineffective. But anyway, my question was, does the research you just presented show that strategy has a different effect on the climate system than having a known quantity of sustained sequestration?
Yes, and so what I just showed is that it does have a different effect on the climate system. It can still have an effect. So I don't want you to walk away from this thinking, okay, we shouldn't be investing in soil carbon sequestration. The point is that absolutely this can have an effect on the climate system, but it will be different if we are not also reducing climate and just making it harder for ourselves. So that to say, the exchange isn't really what we're looking for, but rather both and. Does that make sense?
Yep. Yeah.
Great.
Here's I'm gonna sneak in another question before we shift over to hearing Susan talk. So all these concepts that you were just talking about, do you think they apply equivalently to forests, or do we need to think about additional factors or different factors in the context of above ground natural carbon stocks?
That's a good question, and I'm no expert in forest carbon sequestration. I do think with regards to soil carbon in forests, absolutely these concepts can apply. And I would guess, since we took an atmospheric perspective, essentially these concepts will apply to anything that is removing carbon out of the atmosphere for an impermanent amount of time. So, you know, mathematically what we showed is that, yes, I think it is applicable. It just depends on what you're using as your context.
Great, thanks.
Thank you so much.
Yeah. All right, so we're going to shift gears now, and we'll hear from Susan Crow. And Susan, if you want to, oh, I have to do this. I'll make you the presenter. Did that work? And
there we go.
In just a moment, we'll see some slides. There we go. Oh, I saw it for just a split second, and then it disappeared, actually. It's back. Okay, we're good.
All right.
Okay, so we'll hear from Susan about her work using some basic mathematical theory to understand this in collaboration with Carlos Sierra. All right, Susan, take it away.
Right, thanks so much. And thank you, Dr. Mayer, for such a awesome presentation. I'm so excited to go next and offer up kind of a very complementary, I think, component to this. So thanks so much, everyone, for your time today spent learning more about the meaningful climate benefits of sequestration and our computation for warming mitigation. So I am Susan Crow from the University of Hawaii, Manoa, and first want to acknowledge my co-author, Carlos Sierra, who is the math and modeling brains behind this presentation. He is at the Max Planck Institute for Biogeochemistry and more recently the Swedish University of Agricultural Sciences as well. And acknowledge up front funding from USDA NIFA, the German Research Foundation, and Max Planck Society. So soils are important carbon reservoirs, as we know, but it is challenging to know how long the new carbon inputs from climate mitigation activities will stay below ground and provide those warming benefits that Dr. Mayer just talked about. So carbon, as we know, is not stored permanently, and it's important to understand how long any new inputs will actually persist below ground. So an approach that can quantify both the amount of new inputs and for how long they will remain can greatly help us understand and also help scientists communicate the role of soils as a climate change mitigation strategy. So one problem that I've encountered in the policy-oriented concept of permanence, or one problem I've encountered is the policy-oriented concept of permanence and uncertainty in how long soil carbon stays below ground. I've found sometimes creates a barrier to incentives surrounding soil carbon and climate actions. And so like a leaky bag, when you put carbon into soil, it doesn't just accumulate, but multiple soil processes result in losses. As we know in this group, these include decomposition, leaching, respiration, and thereby kind of creating the holes in the bag that release carbon even as you continue to have inputs. So there are inputs, there are outputs, but in the meantime, there's loss versus persistence, which is a more biogeochemistry-oriented concept that has a connection to that policy-oriented concept of permanence. So linking persistence to the issue of permanence is something that we aim to do. So permanence is something that's been highly debated in carbon sequestration policymaking. And contributing to this debate, there hasn't really been a way to compute the climate benefits in the context of warming units that Dr. Mayer referenced as well. So the climate benefits of carbon in terrestrial ecosystems, even when we have a model for that system in the same units. So the units of GHG emissions often are expressed in global warming potentials. So we can quantify the degree of permanence in soil carbon using existing frameworks of soil carbon stabilization, and persistence in soil biogeochemistry. But we really need to connect the concept of permanence and persistence to the actual amount of warming that is avoided while carbon is stored in ecosystems, including soils. So we've been working on and present here a set of metrics and proposed definitions to sort of assist with this debate and communication and computation of the benefits at multiple scales that are important for really tackling the existential issue of climate change that we now find ourselves facing. And so as an example, we explore the fate of new carbon inputs in two very different agricultural systems. One are tropical perennial grasses that were grown for biofuel, forage, or feedstock in a zero tillage practice in Hawaii in the United States, and the other a boreal, cold temperate, semi-humid agricultural soil from long-term amendment trials in Sweden. So we'll explore for how long the new carbon inputs on an annual basis stay in the different soils and how much warming they avoid while stored, and then how this compares directly, or how you can compare it directly to the warming produced by emissions of fossil fuels, because this sort of push and pull of don't distract from reducing emissions permanently is absolutely important. And this idea that even if the sequestration is temporary, it's really, really important, as Dr. Mayer just showed. It's a really fascinating connection there. And so hopefully these computations will kind of assist with laying out some of those same principles. Okay, so our approach is similar to the computation of the absolute global warming potential, or AGWP, of an emission. For an amount of emitted carbon, the AGWP quantifies the potential warming as the area under the curve of the amount of carbon remaining in the atmosphere over a given time horizon. So until now, there's not been a similar approach to quantify the effects of CO2 uptake on land. So many people are more familiar with GWP of multiple greenhouse gases that often are presented relative to one another in CO2 equivalencies. So the absolute value of these are the AGWP. And so the AGWP of 1 megagram of carbon to the atmosphere is 3.4 times 10 to the negative 10 watts per meter square on a 100-year time horizon. So most carbon dioxide stays in the atmosphere for 300 to 1,000 years. There's a big range. Some stay shorter, some stays longer, which should sound familiar to a soil carbon crowd as well. Some stays longer, some stays shorter. And so we propose to quantify the area under the curve of an amount of carbon uptake over a given time horizon here on the right. And we define this area under the curve as carbon sequestration, or CS, because it's a metric that considers both the amount of carbon uptake and the amount of time it remains stored in the ecosystem. Once we have CS, in addition, we can compute the amount of avoided warming of carbon uptake during the time of carbon storage. And this metric we call the climate benefit of sequestration, or CBS. And it's similar to AGWP, but it considers uptake as a negative emission that eventually returns to the atmosphere. So CS and CBS can be computed for any ecosystem. It only requires a model, simple or complex, that describes how carbon is decomposed in soils. And so the approach works for simple linear models as well as complex nonlinear models that can actually take into account changes that we expect to come over time, as Dr. Mayer also mentioned. So the key is that the AGWP and CBS can then be added together to obtain the net climate effect of simultaneous emissions, which would be positive, and sequestration, which would be negative in a particular system. So CS is a metric computed from any compartmental model. In our example, we use a very simple two-pool model as the storage of a certain amount of carbon input over a period of time as it flows through an ecosystem. Then we use the areas under the curve until a specific time horizon to compare how much carbon has remained for a certain time. Okay, so to put this into the context of the examples, first, we considered the fate of the same amount of carbon input at 1 megagram of carbon per hectare in a tropical perennial grass system in a mollisol in Hawaii versus the arable cambisol in Sweden. On a 5-year time horizon, more carbon remains from that one allocation of input in the Hawaii soil than in the Sweden soil. Therefore, CS was higher in the tropical soil on that time frame. But at a 20-year time horizon, CS was higher for the Swedish cambisol. So although one unit of carbon decomposes relatively fast at first in the Swedish soil, more carbon remains after 20 years in comparison with the Hawaii soil. So time horizon matters. Okay, so then we considered not just one unit of input, but the differences in plant productivity and carbon input between the two sites, and then ran through the same exercise. Because soil from Hawaii has higher inputs from higher crop productivity, the areas under the curve are higher for Hawaii at all time horizons, shown here all the way up to that 20-year time horizon. So we can say that the soil in Hawaii has almost twice as much carbon sequestration from just 1 year. This is just a snapshot of that 1 year of inputs based on productivity in the 20-year time frame compared to the Swedish soil. Okay, so the CS, carbon sequestration, tells us the amount of carbon stored over a period of time, but it doesn't tell us anything of the greenhouse gas effect that carbon avoids while stored in soil. So the next step of the computation is the CBS, which is the radiative forcing effect avoided by those carbon inputs to the soil stored over the period of time. Because most carbon that enters the soil returns to the atmosphere as heterotrophic respiration, CBS actually accounts for the temporary effect of storing carbon that enters a particular time and returns to the atmosphere. Okay, so here, sticking with the same examples, we stay with the productivity-based computation and can compare the potential amount of avoided warming between the two soils at two different time horizons. So now talking about a short-term time horizon, the tropical soil in the dark red line has a larger climate benefit or more negative CBS. But on the 20-year time frame, Hawaii is still out ahead, pulling down more carbon, but you can see the effect is already starting to decline. We found that because inputs are larger in the tropical mollisol, more warming is avoided for the time horizons below about 40 years. But at that inflection point, the temperate soil actually has a larger climate benefit. So it's important to note that all of these curves eventually go back up to zero, but this example is just tracking that one pulse of input. So in reality, each year gets a pulse and it gets summed up over time, but we're just kind of breaking it down so you see how the computations work. Okay, so as the next step, we can now make the direct comparison between emissions and uptake in our example soils. So remember that the AGWP of CO2 is much larger for 1 unit of emission. It's large for 1 unit of emission, and in fact, it's much larger than for 1 unit of sequestration on any time scale, because fossil fuel emissions stay for a much longer period of time in the atmosphere. And so the emission of 1 megagram of carbon to the atmosphere leads to warming that's about 1 order of magnitude higher than the potential warming avoided in either of our example soils over a century. So in the systems as they are, avoided emissions are much more effective than sequestration and the most critical, right? So again, that kind of like push and pull between where do we focus our time, avoided emissions, absolutely. But in the short term, which again, kind of coming back to like this issue of like temporary is still really important that Dr. Mayer points out. This is really, really interesting, right? In the short term, some high carbon input soils can make a difference. And in the long term, more persistent soil carbon is better. So in these systems, they may never compensate directly for emission, but you can start to think about what management action or what would be required through management that could. And so what we found is that by computationally slowing down the decomposition of the fast carbon pool by about a decade in the Hawaiian soil, for example, by adding biochar or making a choice about a site with a high concentration of volcanic ash that may stabilize and increase the persistence of carbon inputs, may avoid a warming effect larger than the warming effect that could be generated by an emission over the course of the century. Okay, so this is really cool because instead of a lot of arguments kind of say like, oh, there's not enough emissions to sort of, I mean, there's not enough sequestration, enough warming benefit in sequestration, and we really have to focus on emissions, don't distract. Actually, you can see in some cases where emissions and sequestration, the warming benefit, meaningful climate impact actually is approximately the same. So it's an interesting point it's an interesting point that helps make a counter argument in the communications. Okay, so these examples, just a reminder, this example is in shallow soils where the least persistent carbon dominates, right? And a full soil profile would be important for a more complete picture of the benefits. Nonetheless, this is a snapshot of 1 year, 1 year of inputs and an instantaneous pulse of sequestration versus a pulse of emissions, just to demonstrate the concept of how these kind of play out in tandem. And so our first take home is that with this example, we showed new carbon inputs do not remain for long time scales, and only small proportions may be stabilized in both soils from Hawaii and Sweden, but it's not nothing. It can be really effective as a climate mitigation strategy in some systems, particularly if we're really focused on kind of immediate actions to really like tamp down those climate scenarios. So until now, there hasn't been a way to compute the climate benefits of carbon in terrestrial ecosystems, even when there's a model for that system in the same units as the GHG emissions are expressed in the global warming potentials. It's really the units that that make this system level comparison possible. And so this demonstrates how AGWP and CBS can be added together to obtain the net climate effect of simultaneous emissions and sequestration in a particular system. The amount of inputs are affected by land use and management changes like deforestation, afforestation, conversion of pasture to conservation, removal of crop residues, etc. But the amount of time carbon inputs remain in the system is also affected by management choices that influence persistence, like site selection or some of those soil amendments. Okay, management decisions that factor in both inputs and persistence can maximize climate change mitigation potential. Okay, we have a more broad, expansive application of the computation as well to really kind of put a finish to this fantastic seminar. I'm super excited to pull all of this together. So now we have a way to compute the climate benefits, but that more expansive application contributes to the conversation as well, because at a broader scope and scale to just CS and CBS, there's a systems level life cycle analysis approach to climate action planning. And this encompasses not only carbon and warming potential, but all of the co-benefits to environment and society that come from implementing these best management practices. For example, soil health and human well-being. So currently emphasis is on an inventory, GHG inventory framework for climate action. This focuses on achieving reductions within jurisdictional boundaries instead of actual impact to the atmosphere. As a result, you can have emissions leakage, so an increase in emissions outside of a jurisdiction caused inadvertently by policies applied within the jurisdiction. This essentially can offshore emissions to another place, often where there are no or lesser regulations, and the climate and other environmental impacts are in fact worse, and this is very problematic. And so one solution to this is that instead a GWP framework, which is a systems level framework for climate action planning, focuses on achieving impacts to the atmosphere through a life cycle analysis or cradle to grave approach to assessing carbon neutrality. Once again, the GWP approach has only been able to account from the perspective of emissions and not the other direction, from atmosphere to land. And so now CBS can contribute uniquely to life cycle analysis that incorporates both GWP and CBS into the computations. LCA is really commonly used in engineering and bioenergy production, and increasingly used in sustainable food systems and the circular economy. Terrestrial ecosystems, agroecosystems, forests, etc., are embedded within these broader social, ecological, economic systems. And so this makes a really important advancement in our ability to really think about meaningful climate benefits. So in the systems level assessment, there's often a need to directly compare the benefit of sequestration to direct emissions avoidance elsewhere within the system. CS allows you to compute how much remains and for how long it stays. CBS allows you to assess the carbon and climate benefits of carbon drawdown into natural and working lands, these forests and productive systems. Then CBS can follow on facilitate direct comparisons about climate change mitigation potential in complex systems. For example, soil carbon sequestration and improved management, and also avoided imports of food fertilizer in a sustainable food system. Since food systems account for approximately 1/3 of global emissions, with energy and transportation accounting for most of the rest, we may not achieve marketable levels of warming potential from soil carbon sequestration, but it's not none, especially in deep soil and high potential soils. But with this context embedded within bigger system level assessments, implementation of climate smart practices and land management decisions come with a multitude of co-benefits to the environment and society, including soil health, reduced dependence on imports, clean water, and local jobs. And so CBS provides that missing piece that quantifies warming benefits of sequestration alongside avoided emissions within those complex systems. And so therefore investments back into the community build viable social, ecological, economic systems that policy and programming can better can embrace and fully support. And so even if, I guess to bring it back to Dr. Mayer's kind of conclusions about virtuous cycle, so simultaneous avoiding emissions and carbon sequestration really resonates with this context as well. And then even if the sequestration in soils is temporary, it's still really, really important. And so part of that is that you're implementing these best management strategies, even if the soil carbon sequestration in of itself begins to decline, you've still invested in these management strategies that build resilience into communities and landscapes around the world. And so I will end there and ask if you guys have any questions. Stop sharing. Thank you.
Thank you. That was terrific, and I think it meshed really well with the first talk. This is a great pairing.
Super cool.
All right. For those in the audience, feel free to post questions via the questions feature, and I'll start off with a question that's connected a bit to something you mentioned about deep and high potential soils. I'm wondering if you could speak a bit more about that. There was some interest in that topic in the registration survey. What about deep soil? And if we think about deep soil, how does that change our perspective on this?
So there's lots of discussion about what the net carbon outcomes of deep soil will be. And so I think that there are some deep soil systems that fall into this category of high potential sequestration. And we talked a little bit about achieving thresholds at the high end of carbon, but there's also a threshold at the low end of carbon. And so even the most degraded soils don't ever have zero carbon, right? So there's always this low threshold up to the high threshold. And what we found in some of our systems in Hawaii, deep tropical degraded soils, which are persistent, not just in Hawaii, but globally, these are some of the high potential soils. They're at their low threshold. Implementing a zero tillage system can get them back on that upward trajectory very, very quickly. And so in the examples that I gave, we focused just in that surface soil, but we've shown when we've taken deeper soil carbon that it's actually the deeper areas that have the most soil carbon increase, which is not what we always find in other systems. We find priming that actually releases soil carbon, but in these deep tropical soils that are degraded, which exist all around the world, people are looking to those soils to say, okay, these are the degraded systems. Are they high potential carbon soils? Are those low hanging fruits to really target for restoration? And what we've shown in some of our studies here in Hawaii is absolutely that's where the soil carbon accumulates, not in the surface soils. And so it really just depends on the soil, but so those soils do exist out there where deep soil can accumulate and not actually have a net loss with priming.
Great, thanks. I guess a related question. So the two examples you gave were at these different latitudes, and it seemed like they behave very differently for reasons that may be generalized. That in lower latitude environments, at least where the climate's wet enough, productivity is high, and that changes the way the system functions. So do you think that simple pair of examples that you presented tells us something more general about the difference between focusing on low latitude versus high latitude systems?
I think that there's some generalizability and sort of the ability to apply these computations to simple models, right? So soil biogeochemists love to have really, really detail, a nice balance between detail, but simplicity, but models that really, really work well for our specific systems, but lack that general applicability. And so I think there's hope for it, right? And the buffers that we discussed often are generated from uncertainties that come out of these soil carbon models, right? That's where the buffer calculation comes from. And so the better model, the lower the uncertainty, and therefore the more value you can get out of your system, because in its most simplified sense, the buffer applied to your system can be smaller, right? And so really nailing those uncertainties, reducing the uncertainties, really getting greater certainty is important, but not always, right? Like getting the simplest model possible that does encompass these really, really critical details, really critical, not details, but big picture efforts, I think is the balance that we need to aim in this like really fast moving policy area, right? So when we can generalize, we should, and that's one of the challenges, right, for us is to be kind of looking to where can we get things moving in the right direction as quickly as possible without doing harm. We don't need the most fancy complex models, although if you have one, this computational structure allows you to use even the most complex model versus the simple model. And so there's a lot of flexibility, generalizability built in.
Thanks. So to follow up on that, it seems to me that these calculations, they need some kind of a model, whether it's a simple or a complex one. How do they relate to our measurements? Do they, does this point towards some direction in terms of how we should be measuring soil carbon and the climate effects of soil systems?
Yeah, everybody's always seeking the measurable, modelable pools, right? Like that kind of perfect trifecta of measurements, models, and kind of the concepts, right? And that's going to remain tricky. And I think that as many of us are really starting to think about the commodity base, and not necessarily carbon as a commodity, but how to support the producers to implement practices that would have these climate outcomes. I mean, what do you have to measure in order to verify that we're achieving these climate benefits? A really good question, and we're almost out of time, so we'll have to I'm just kidding, but this is one of those difficult questions, right? Like, how much measurement do you have to do to verify that you're achieving these climate benefits? And I think that that's going to be regionally dependent. It's going to be entirely dependent on what people's capacity for making those measurements and verifications are. But I think kind of the more we can kind of get our heads wrapped around the concept of directional correctness, like getting us moving in the right direction. So Eric, you were always kind of quick to say, like, magnitude doesn't matter, we just need it like to be in the right direction. Like, we just need it to be headed in the right way and do it as quickly as possible. And that's really where I always kind of fall back on all of those co-benefits. As long as we get the soil carbon, ecosystem carbon moving in the right direction, we also build health and resilience into soils and landscapes. And so I think the more we can kind of help ourselves move in that direction, and that carries over to the measurements and verification protocols as well, right?
Great. All right, well, we're coming up on the hour here. And so I think we'll stop there, but thanks for answering all those questions and sharing such a wonderful talk. These are both terrific seminars. So anyway, thank you all for joining today, and the recording will be up as soon as possible, and we hope to see you next month for our next webinar. Stay tuned for advertisements. All right, see ya.
Thanks, Eric.